Welcome to the first GSMOD tutorial. I will start this tutorial by explaining what GSMOD is. GSMOD is a software that allows users to run MODFLOW and MT3D models using probabilistic flow and transport parameters, which leads to stochastic modeling results. One of the key aspects of GSMOD is that it is extremely easy to use, allowing users to add stochastic modeling capabilities to any model that relies on the official MODFLOW and MT3D codes. In that sense, modelers can work as usual using their preferred groundwater modeling software and take the decision to include stochastic modeling towards the end of the project only if they have enough time and budget. Here we can see an example of the type of results that GSMOD is able to generate. It is basically a stochastic concentration hydrograph that is showing the results of 1000 model runs with concentrations in the vertical axis and time in the horizontal axis. As you can see, GSMOD is able to separate the stochastic runs that are considered to have a good calibration, the lines in darker blue, from the ones that are considered to have a bad calibration, the lines in lighter blue, based on a user-defined criteria, which in this case is a normalized root mean square error higher or lower than 10%. GSMOD is also able to add a confidence band, which is the red area on top of the graph, based on a user-defined percentile, which in this case is between 5 and 95%. GSMOD is also able to display observation data and the best calibrated model, which is the thick segmented blue line. These types of stochastic results are considered to be extremely useful, especially during the predictive simulation scenarios. In this specific case, we can conclude that the maximum concentration in this specific borehole will be around 1100 mg per liter if we consider only the properly calibrated realizations, and around 1600 mg per liter if we consider all realizations. We can also notice how the degree of uncertainty changes with time, with very little uncertainty at the beginning of the simulation and a fair amount of uncertainty towards the middle part of the simulation. More than 300 mg per liter in this case. One of the main objectives of GSMOD is to overcome the limitations of using deterministic models, especially during the traditional sensitivity analysis stage. Let's start now with the first GSMOD tutorial. The first thing that we need to do is to open the tutorial document, which is located within the tutorial folder. There are two versions of the tutorial, one in English and one in Spanish. We can also see 4 subfolders within the main folder. The contents of these folders will be explained as we move forward with the tutorial. The objective of this tutorial is to add stochastic modeling capabilities to an existing flow and transport model that was built using Groundwater Vistas 7 from ESI. It is not necessary to open the Groundwater Vistas model in order to develop this tutorial. However, if you would like to open the model and don't have a Groundwater Vistas 7 license, you can go to groundwatermodels.com and download the Groundwater Vistas 7 installer, which comes with a free student license. The link is available in the tutorial document. Permission from Jim Brombo from ESI was given in order to include a Groundwater Vistas model within the tutorial. Now, a little bit of background information about this specific groundwater model. It is basically a flow and transport model that was built in 1996 by Little et al. In order to study the movement of a chloride plume associated to domestic and industrial sewage coming from 2 lagoons located to the north of Royston in the United Kingdom. The plume is moving to the north within a chalk aquifer which has high transmissivities associated to conductive fractures. Although the chalk has a high primary porosity, the pores do not contribute to transmissivity because of their very small size. That said, there is chloride diffusion happening between the fractures and the primary porosity, which induces retardation in the movement of the plume. This behavior is represented in the model by activating the dual porosity approach in the transport package. Groundwater discharges in the north side of the model through springs, brooks, and rivers due to the outcrop of the aquifer basement. Now that we know a little bit about the hydrogeological context of the model, let's start the GSMOD project for the calibration period. The first thing that we need to do is to create a new GSMOD project by going to the File menu and clicking New Project. Define a proper name and save the GSMOD project in the tutorial folder. In this case, we will name the GSMOD project as Model Cal. Now we have to go to the Inputs menu and click on General Parameters. The first thing to do is to activate the stochastic transfer capabilities in order for us to run stochastic realizations for both the flow model and the transport model. We will leave the initial number of realizations with the default value of 50. New realizations can be added at any point of the modeling process. We will also leave the maximum running time with the default value of 24 hours, since the requested number of realizations will run in a much shorter time frame. Now we have to look for the MODFLOW and MT3D MS name files of the calibration model by going to the stochastic calibration model folder. The MODFLOW name file is called cal01.num. Meantime, the MT3D MS name file is called cal01mt.num. Finally, we accept the changes. Now we have to go to the Inputs menu again and click on Stochastic Parameters in order to set up all the flow and transport parameters that we want to consider during the simulations. In order to make things easier, 2 Excel spreadsheets with the necessary information are already included within the tutorial folder, so we are just going to import them into GSMOD. We click on Import for the flow table and look for the requested spreadsheet, which is located in the Excel spreadsheet stochastic parameters subfolders. In this case, we have to choose the flow parameters file for the calibration period. We do the same for the transport parameters. The tables that we imported contain all the stochastic parameters that we want to include in the flow and transport models. For example, the first parameter that we want to consider is the hydraulic conductivity of zone 1 along the x-axis. In that sense, the name that we have chosen for this parameter is kx1. The type for this parameter is kx, and we say that it follows a triangular distribution with a minimum value of 5 meters per day, a maximum value of 20, and a mode of 10. The internal code of 901 that we have chosen for this parameter needs to be replaced in the respective flow parameter of the original MODFLOW model. In that sense, if we go to the Groundwater Vistas calibration model located in the Model Stochastic subfolder, we will notice that a value of 901 exists as hydraulic conductivity along the x-axis in Zone 1 of the hydraulic conductivity database. This simple yet powerful approach makes GSMOD compatible with any modeling software that relies on the official MODFLOW and MT3D MS codes. The Groundwater Vistas model located in the Model Stochastic folder contains all the appropriate codes for the defined stochastic parameters, and it was already translated. We click Accept to save the changes. Now we have to go to the Inputs menu again and click on Calibration Data in order to set up the flow and transport targets that will be used by GSMOD to calculate the calibration statistics of all valid realizations. Again, 2 Excel spreadsheets with flow and transport targets are already included within the tutorial folder, so we are just going to import them into GSMOD. We click on Import for the flow table and look for the requested spreadsheet, which is located in the Excel spreadsheets Ops Data subfolders. In this case, we have to choose the targets data for the flow model. We do the same for the transport targets. The tables that we imported contain all the necessary information to characterize the observed values: name, location, weight, time of the measurement, and value. We also need to provide the grid offset values along x and y, which are the coordinates of the lower left corner of the model. This information is provided in page 6 of the tutorial. Finally, we change the flow calibration criteria from 10% to 5%. We click Accept to save the changes. Now we have to go to the Inputs menu for one more time and click on Mass Balance, Executables and Solvers. We will leave most options with the default values. However, we do need to look for the specific MODFLOW and MT3D MS executables that are going to be used by GSMOD to run the models. These executables are located within the GSMOD installation folder. In this case, we select MF2005 for the MODFLOW code and MT3DMS5B for the MT3DMS code. The user is also able to change the limits for the flow and transport numerical balance errors, which will be used by GSMOD to detect and filter out models that have numerical issues. The user can also activate the heuristic solver approach, which detects when a model fails to converge, rerunning it with more robust solver parameters. Finally, the user is able to change the number of CPU cores that will be used by GSMOD to perform parallel runs and to post-process the results. We click Accept to save the changes. Now we start the stochastic simulations by clicking on the Start GSMOD button. Messages will appear on the lower left corner of the main window explaining the current status of the modeling process. Flow and transport calibration statistics and numerical balance errors will be displayed on the 4 charts located in the main window. The user can stop the simulation at any point by clicking on the Hold Simulation button, which will tell GSMOD to finish running the last batch of models. We will click on this button now. The user can post-process the results at any point to verify that GSMOD is calculating the expected values. Let's generate the concentration hydrograph that we saw at the beginning of the video. We go to Results, Hydrographs, Concentrations, and we import the locations where we want to generate the hydrographs. Again, spreadsheets with the necessary information are included within the tutorial folder. We click on Import and we go to the Excel Spreadsheets Ops Well Locations subfolder and we choose the Ops Trans spreadsheet. Finally, we press the Process button to generate the hydrographs for all the specified locations. The resulting plot can be exported as an image, meantime the numeric results can be exported to Excel. Now we will add more realizations to the project by clicking on the Add Realizations button. While GSMOD is running, we are going to answer a few questions. The first question is, are the stochastic running times compatible with commercial projects? I would answer yes, they are. First of all, as we can see, GSMOD is able to run models in parallel, which considerably improves running times. In the future, distributed computing capabilities will also be added, which will improve running times even further. In addition to this, it needs to be considered that the stochastic modeling process will usually begin when the numerical model is already calibrated and when a set of deterministic predictive simulations are already finished. This means that it is very likely that the user won't need to modify the numerical model nor the conceptual model while working on the stochastic simulations. In that sense, the user just needs to set up the GSMOD project and leave the computer run the stochastic simulations while working on other parts of the project, for example on the modeling report. That said, it is always important to develop models with relatively short running times and that do not have important numerical issues. The second question is, how do I get the necessary field information to characterize the probabilistic distributions of the flow and transport parameters? It is very likely that a common hydrogeological project won't have enough information to fit distributions to the selected flow and transport parameters. The usual approach is to rely on triangular distributions which require a minimum, maximum, and most likely value, which is information that a conceptual model will usually have for the most relevant parameters. Now that GSMOD has finished running the stochastic simulations, we can revise the available post-processing options. Let's go again to Results, Hydrographs, Concentrations to revise how the concentration hydrograph looks with the new realizations. As more realizations are added to the project, more accurate probabilistic results are obtained, within certain limits. The total number of realizations that will be required depend on the complexity of the model, the number of stochastic parameters that are being used, the parameter distributions, and the type of predictions that are being evaluated, among others. We click Accept to save the changes. Let's go to Results, Maps, Concentrations to generate probabilistic maps of the stochastic realizations. The first type of map that we are going to create is a probability of exceedance map that will show the probability of exceeding a chloride concentration of 250 mg per liter at the end of the simulation period. We change the type of map to probability of a variable being higher than certain limit. We write 250 as that limit and we press Process. Contour lines showing the probability of exceeding 250 mg per liter will appear on the map. Now we are going to add shapefiles of the different boundary conditions in addition to a satellite image. Click on any of the available map layers and look for the files which are located in the Maps folder. We start by adding the no-flow boundary conditions, followed by the drains, the general head boundaries, and the recharge areas associated to the lagoons. We can change the colors, the levels of transparency, and the sizes of any of the added shapefiles. Finally, we add the satellite image. The coordinates for georeferencing the image are included in page 11 of the tutorial. The map can be exported as an image, as an animation, or as a raster. The second type of map that we will create will show concentration contours that include 95% of all realizations at the end of the modeling period. We change the type of map to contour percentile value, we write 95 as the percentile value, and we click Process. We can change the limits of the contour bar in order to get more useful labels. We set the maximum value as 4500, the minimum value as 0, and the number of contours as 9. Again, we can export the resulting map as an image, animation, or raster. The users are free to explore the remaining post-processing options on their own. Now we are going to set up a stochastic project for the predictive simulation period, which will use the GSMOD project that we created for the calibration period. We save the current project by clicking Save in the File menu. After this, we create a new project with the name modelsim.gmt. The steps to set up the new project are the same as for the calibration model, but using the MODFLOW and MT3D MS models associated to the predictive simulation scenario. For the stochastic parameters, we import the spreadsheets associated to the predictive simulation. The first thing that we notice is that many of the stochastic parameters are set to be taken from a previous GSMOD project. This means that for each of these parameters, the exact values of the calibration period will be used for the predictive simulation period. For example, if kx of zone 1 had a value of 12 meters per day for the realization 1 of the calibration period, the same value of 12 meters per day will be used for kx1 of the predictive simulation. We see that only the parameters associated to the infiltrations of the stress period 4 will be generated by GSMOD during the predictive scenario. We need to activate the simulation based on a previous model option and look for the previous GSMOD project by selecting Model Cal as the requested file. After this, we need to look for the MODFLOW and MT3D MS working folder of the calibration model, which will be automatically selected if the user hasn't changed the working folder location. Finally, we check that the use of initial conditions based on a previous model are active. These options indicate GSMOD to automatically update the initial conditions of each predictive realization using the last saved time step of the respective calibration model. We click Accept to save the changes. If we go to the Calibration Targets menu, we will see that most of the options are deactivated. This happens because GSMOD uses the statistics of the calibration models to filter out the poorly calibrated realizations during the post-processing of the predictive simulations. Finally, we need to set up the MODFLOW and MT3D MS executables in the Mass Balance, Solvers and Executables menu. We click Start GSMOD to start running the stochastic realizations for the predictive period. The total number of predictive simulations that can be run are limited by the total number of calibration runs. In order to run more predictive simulation models, additional calibration models would have to be run. The users are free to try the post-processing options for the predictive simulation on their own. Finally, the most important conclusions associated to the use of GSMOD are presented. GSMOD can add stochastic capabilities to any model that uses the official MODFLOW and MT3D MS executables. The procedure is completely independent of the original modeling software. The stochastic results generated by GSMOD are extremely useful for studying and reducing hydrogeological uncertainty. More information about GSMOD can be found at gwmodeling.blogspot.com or by sending an email to support@gsmod.net.